and South Asia Engineering Center. He worked in GE Power and Water as a design engineer for 2 years. He did his master's from IIT Bombay and also is a student advisor. He's a member of the Digitalization and Computational Mechanics Working Group. Please welcome.
Thank you very much. So at the outset, I would like to thank Professor Dinesh.
A tick on everything there.
Kind of. I can add a few more if you want. Thank you very much, Professor, for inviting me to this workshop. And in fact, I would like to congratulate you both on this joint collaboration. I'll be more than happy to support you in whichever fashion. So one of your students was asking me, am I an ISC alumni? There is a story behind it. In fact, I was probably supposed to do masters here. I probably was eligible, so my gate rank was pretty okay. But my interview was scheduled on the same day my bachelor examination was. So I wrote to Vice Chancellor in ISC. I also wrote to President of India then, Dr. Kalam, can I get any leeway to attend the interview later? But obviously, academics doesn't work that way. So I happened to do my master's in IIT Bombay. I don't regret that decision, but it was, I got an opportunity to work with one of the fracture mechanics stalwarts, Professor Maiti, who works very closely with Professor Nassimman from ISC. So let me probably with that, let's get started. So what you want to see over the next 30 minutes, I have around 25 slides or so, and I hope I'll keep you all awake. So that would be my challenge going forward. So over the next 45 minutes, I'll take you through how in Airbus we are establishing advanced structure simulations as a potential means of compliance and establishing that as a credible alternative to the physical testing. What you see over here is A350-900, a cutting-edge new technology aircraft, which has more than 53% of composites by weight, undergoing its full-scale static test. You can actually see the wings of the aircraft bend by more than 7 meters under ultimate loads. What you see now is a full-scale virtual testing model superimposed on the physical aircraft. And you guys see the physical aircraft here. It probably shows the very good correlation we have achieved between physical and the virtual testing. Obviously, here it talks mostly about the global displacements, but I'll probably talk about the confidence we have gained in terms of predicting the local behavior as well very closely. So before getting into the topic of our interest, which is advanced numerical simulations, I will probably give a very brief overview about Airbus. Then I'll talk about the technology, the vision, and how are we going to achieve it going forward. So Airbus, I believe, probably doesn't need recognition, especially for those who are well versed with the aerospace industry. It's a world leader in the commercial aircraft segment and a global pioneer in general for the aerospace industry. Right? And we have, as you can see, a product family ranging from A320, which we got it from Bombardier to revive the program. Then we have A320 family, which probably is the best-selling aircraft in the history of commercial aviation. Then we have the ever-reliable A330 and the new technology A350. And last but not the least, my personal favorite, and I worked a lot on this aircraft, the A380. Sorry for the interruption. No problem. Yeah. So I was talking about the A380. It obviously was loved by everyone for the comfort and the noise levels it produced. Unfortunately, it wasn't a commercial success, and we had to stop the production of it a couple of years back. So I'll be more than happy if the market demand kind of grows again and if Airbus decides to reintroduce that into the market. So I have a very cool stat which says that every 1.5 seconds, an Airbus aircraft either takes off or lands, thanks to more than 14,000 aircraft which are in operation. And I'm very sure this stat will only get better and more cooler as we have more than 7,000 aircrafts to be delivered to several airliners over the next decade or so. So having talked about Airbus in general, I want to take you to association of Airbus with India. It all started in 1970s, even before I took birth. By the way, I'm not that old. So, and after that, Airbus did not look back. Currently, we command more than 70% of the fleet share and more than 60% of the order share. And recently, as you know, Airbus secured a massive order from Air India, and these figures doesn't account for that. And in the year 2007 is when Airbus got into India and launched an engineering center. Now we have more than 1,200 engineers working on cutting-edge technologies such as advanced structure simulations, fluid dynamics, simulations and physical systems, avionics software, so on and so forth. Just to name a few. But the fact that we probably can be quite proud at Airbus is that almost every aircraft is partly manufactured in India, and I would say this proportion is only going to go up with the push Indian government is placing on the major OEMs, through Make in India initiative, and Airbus is very much committed to further it going forward. So coming to the topic of sustainability. Looks like there is someone else speaking there.
You asked a question about repeatability.
Absolutely. Coming to sustainability, currently aviation industry is contributing to more than 2% of the global man-made CO2 emissions. And Airbus is committed to reduce it and to make aviation industry sustainable, and is committed to 2050 net zero carbon emission compliance. This is obviously in line with the Paris Agreement to limit the global emission to 1.5 degrees Celsius. But if you look at the history says that, in fact, if you look at the relative fuel burn per seat, right from 1950s to now, there has been a substantial reduction in the fuel burn, thanks to introduction of advanced technologies. In this case, it's composites. As you can see, there is a significant increase in the composites from the start of this century. Now we have more than 50% of composites with weight in A350. So in order to achieve this particular figure, Airbus has recently came up with zero emission initiative, wherein it has launched 3 concept aircrafts. As you can see, most of them are regional aircrafts, and all of them powered by hydrogen. In fact, it's a hybrid hydrogen technology with hydrogen fuel cells and hydrogen powered engines. And this is where, according to me, we are going to introduce many advanced technologies, be it ALM products, be it functionally graded materials. And according to me, in order to industrialize it, advanced structure simulations is going to play an instrumental role going forward. And that probably sets up today's talk on numerical simulations. And just for the student community, probably professors who already know about the evolution can bear it for a couple of minutes. So it all started, as you know, from 1950s, when the first paper on FEM is launched or released. I would encourage the student community to read this paper. In fact, this paper also has the recommendation sections, and probably the author Turner probably has great foresight. He has recommended improvements to this technology, and I can tell you many of them are in place now. And needless to say that this technology obviously has weathered the test of time and grown by leaps and bounds. And after the introduction of the commercial software, NASPLAN, I would say industry has adopted it, and currently we are using finite analysis significantly during the product life cycle. And at Airbus, we have been using linear and conventional FEA from 1970s, but I would say from 2005, the usage of advanced NLFEA has seen a significant increase. And currently, we are actually looking at even developing non-linear FEA as a potential means of compliance by developing simulation governance at the industry level, which I'll talk about later. And we are also looking at augmenting the simulations using AI and ML technologies as well. So you all must be wondering, I mean, when will the topic start, right? Probably I think this is where the actual topic starts. The definition of virtual testing, according to me, is a representation of structure and predicting the structural integrity under diverse loading conditions using advanced nonlinear FEA. And smart testing and simulation is actually a marriage, according to me, between physical testing and virtual testing. You can see the word smart, right? I'm not really sure, whether people will agree if you say getting married is a smart move, right? But for the industry, this is where physical testing and virtual testing can support each other. I'll talk about it later, how they support each other, but probably in simple words, physical testing helps in developing virtual testing methods. And virtual testing, especially at the upper level of pyramid, supports physical testing in terms of de-risking them. So we are talking about a significant increase in the cost and complexity as we go from coupon to a full-scale aircraft level. Can anyone tell me a rough order of magnitude cost of an full-scale aircraft testing, which you saw on the opening slide, wherein A350 was tested for certification? Rough order of magnitude. Yeah, obviously gross for sure. just some number in millions. Okay, 300 to 400 crores. Okay, right. Anyone? So we're talking about potentially much more than 100 million, depending upon the size of the aircraft. But probably if you talk about even the smallest of aircrafts, we're talking about more than 100 million aircraft. 100 million, and it is extremely important that we execute it properly. This is where virtual testing in Airbus has been playing an instrumental role in identifying all the unforeseen structural issues during the physical testing and support glitch-free certification of the aircraft programs. And once we have the virtual testing, it will not just limit to the development, right? It can also be helpful when we have any in-service issues, potentially on the static side or on the fatigue side, to understand the root cause of in-service issues, and probably can even lead to design optimizations going forward. So, as I said before, we use linear and conventional film analysis. We use advanced nonlinear FEA. Linear FEA is mostly used during the sizing phase, during the design phase, where the structure is sized to approximate dimensions. And later, advanced FEA is used to validate the structure, to identify whether we have any unforeseen structural issues in the structure or not. So if we look at the usage of virtual testing, when I mean virtual testing, I'm talking about advanced nonlinear FEA, is mostly used in the certification phase to de-risk structures and to support the first flight, so on and so forth. And once we have it, we can also support the in-service operations of the aircraft. But going forward, it will be very different. I'll talk about it when I share the vision. So this slide talks about the increase in the usage in terms of scale. So it all started in 1990s when nonlinear FEA was used for the first time on a subcomponent level to address an in-service issue. Then we moved to a portion of the wing here. You probably can say a subcomponent. Then we moved to component to develop A320 Shacklet aircraft. I'll talk about these two in the subsequent slides. And a decade earlier, we have used advanced NLFEA at the aircraft level. So we are talking about potentially more than 70 million degrees of freedom. I've seen Xavier presenting a model which has 3,600 elements. Yes, the first one. Yeah. So this one, probably you can multiply that by 1,000. But I think this exponential increase was only possible due to advances in the computational capabilities. And we should also give due credit to analysis of a capability. It's a commercial off-the-shelf tools I'm talking about, and the validated methods and processes within the organization. And I would say last, probably the most important, is the people skills and the experience we have gathered to use such advanced numerical simulations in the industrial context successfully over the last, I would say, decade and a half. We have also partnered with several commercial off-the-shelf tools. In fact, we did a benchmarking in 2005. We assessed many commercial off-the-shelf tools without taking their name, and we tried to benchmark them against the quantities of interest generally we need to assess the structural integrity. And we happened to select Abacus, for advanced numerical simulation. But having said that, the usage of Nastran is significant in the linear FEM domain, as I just mentioned before. What is also very important is to have a structured and a consistent approach to assess the structural integrity. And in Airbus, we use a multi-scale analysis approach. We start with a very coarse aircraft level model. We subject that to loading conditions, diverse loading conditions it can experience in the field. Then we deep dive, try to understand the local structural behaviors much more closely. So generally, the aircraft and the component level models are used to identify structural hotspots. Potentially, it may just identify the hotspots, but we probably may not understand the root cause of it. This is where we probably need to deep dive further. And we have, as you can see, the level 3, 4, 5, and the detailed models, wherein we capture the structure much more closely, both in terms of physics and geometry, to understand the phenomena very closely. What you can actually see is, as you go from, say, level 0, level 1, we increase the fidelity of your models. But in the industrial context, it is not just important to have an increase in the fidelity. What is also important is to have a validation of each and every fidelity. And this is where we carry out physical testing, as you can see, at the coupon detail level, subcomponent level, aircraft level. So every level, what you see here, has a corresponding physical testing level, which is used to validate the fidelity, is what we use here. It is extremely important to identify the structural hotspots, refine them, understand the root cause, and potentially lead to design optimizations if we identify any unforeseen issues. So here we're talking about structural hotspots could be caused by buckling, could be caused by potentially in-plane through thickness interfacial hotspots, and when we kind of accurately predict the structural behavior, the root cause may be found to be, it could be delamination, debonding of composite structures, or out of plane deformations, which will lead to global instability of the aircraft. So here, the message which I wanted to pass on the previous slide is mostly the rigor we place in the industry on the validation of every level of multi-scale analysis and every fidelity in terms of representing physics and phenomena. So having talked about non-NLFEA, probably I need to also ensure that I keep audience awake. I would like to give you some success stories. Probably you can connect to them better. So I talked about A380, right? How many of you know A380 here? All of you? Are you guys aware of A380? Right. So I mean, this probably we all talk about A380, about the noise levels, the comfort levels it offers to the passengers. But an incident which happened during the development of this aircraft, during the full-scale static test of this aircraft, the requirement generally is to demonstrate ultimate load capability, which is generally 1.5 times the limit load, if you all are aware, right? And it is roughly 2.5 times the operational load capability, operational loads which the aircraft undergoes, right? But the requirement is quite stringent. And during the physical full-scale testing, both the wings of the aircraft failed 3% lesser than the ultimate load. And this happened in 2005. That's when we didn't have the capability of advanced nonlinear FEA then. This kind of situation
We can't hear your voice, sir. Hello? We can't hear the voice.
probably I'll start with the slide again. Is that okay? It is interesting enough for you.
Take two.
Exactly. So this is one of the important success story for Airbus, which actually led to increase in the usage of non-LFEA. This happened during the development of A380, when the requirement, as I said, was to demonstrate ultimate load carrying capacity. But during the full-scale testing, both the wings of the aircraft failed just 3% lower than the ultimate load, and was also reminding you guys about the cost of the physical full-scale testing. But more than that, the complexity. If you want to redo the test, potentially may delay the program by, I'm not really sure, probably months or years even, which obviously, an organization like Airbus cannot afford. This is when we have developed subcomponent level models, as you can see. Probably you guys can predict what kind of behavior is it on the top cover. I think Xavier has already talked about it. As you can see, we have seen significant buckling. It all started with the local buckling, and then you can see almost global buckling of the structure, affecting different portions of the cover. And it's the advanced non-linear FEA simulation which actually helped us not just to predict this, but also understand the root cause. And here you probably can see here that it is a fastener failure between the stringer and the top cover, which actually led to an increase in the unsupported length between the stringers, which led to top cover buckling. And this was almost 1.5 decades earlier. And we presented these results to the certification authorities, the EASA and FAA. And we also demonstrated the very good agreement which we have seen between the virtual testing and the physical testing in terms of predicting the local strains in the vicinity, because that is extremely important. You might probably demonstrate it using, say, nonlinear FEA, but what is the credibility that that's the fact? This is where the validation actually helped us to gain their confidence, and we were able to avoid the retest of A380. And numerical simulation was used to optimize the structure, and without the test, we were able to certify the aircraft. So according to me, this probably was a watershed moment, for Airbus, and it has significantly increased the usage of advanced NLFEA in Airbus. And I need to also mention that this was before I joined Airbus, so I don't have any contribution to it. It's in fact Morten who led this program, and I think make it work for Airbus. And I'll talk about one in which I'm involved. So this was during the A320 Sharklet development. I'm pretty sure many of you might fly in the regional A320s. By the way, I think 80% of the regional aircraft are A320s in India. So I'm pretty sure most of you probably might have traveled. And around 2012 is when Airbus decided to add these Sharklets, or the wing tip devices, to reduce aerodynamic drag, so on and so forth, and improve the fuel efficiency. But that significantly increases the load on the wing in the vicinity of these wingtip devices. And considering the fact that A320 was already an established aircraft, we used nonlinear FEA to assess the structural integrity of the wing. And there probably was a question again that, okay, you demonstrated it at, say, at a subcomponent level, and how can we ensure that the results which you produce at the component level to be credible again, right? So that's when we launched a test, a wing level test in the UK. And we, in fact, took a challenge of predicting the failure load, mode, and location before the test. So it was mostly a blind test prediction, which we did before the physical test. So we communicated the results, in fact, a couple of weeks or probably a week before the physical test, which happened. And you can see this is a kind of model, the wing level model, which we developed. And for your information, you can see the boundary modeled with the actual machine structure. So no enforced displacements. And that significantly impacts the behavior which you predict near the root. Right? And you can see here one of the critical failure mode which we have predicted using the non-FEA. And the failure mode, as you probably can see, the opening of due to top cover buckling, the opening between the spar and the top cover was predicted in the virtual testing. And we predicted this before the test, so before the physical test, and we in fact even kind of erected a camera to observe this location much more closely. And we in fact were surprised, with the level of correlation which we have achieved and the very good agreement, all in terms of load, mode, and the location. And that kind of gave us confidence to move much higher and use aircraft level models actually. You can actually see the aircraft level model which we built here. This is for A350 development to tackle the development challenges of A350-900. As I said, A350 has more than 50% of composites by weight, and a lot of novel designs have been used during the aircraft development. And last but not the least, this was an aircraft program which probably a full-scale aircraft program after A380, and Airbus obviously cannot afford to undergo similar challenges as it did during A380. So this is the model which I was talking about. In fact, we were told that this was probably even is the biggest nonlinear FEA model ever built, not just in the aerospace industry but across industries. And we are probably talking about more than 15,000 components modeled very accurately, the interface between them modeled very accurately. As I also said, this is a graph, as you can see, wherein each dot actually corresponds to the strain which we predict in the simulation, and we correlate against the physical test. And these bands, what you see, are plus minus 10% bands, and you can see majority, almost 96.9%, 97% of strains of a wing level model, and you can actually probably appreciate the details here, right? You can see the stringers model as closely as possible. What you're actually seeing over here is a level 1 component level models. We have built much detailed models to understand the behaviors more closely. And you can see the kind of Yeah. So just to continue. So the models what we developed for A350-900 during its development can capable of predicting all these different failure modes. But if you probably observe very closely, we have all the complex failure modes, composite bonding, buckling instability, material failure, fastener failure, so on and so forth. But there is one failure mode probably which is missing, which we are still, I would say, working very closely with academia to master, which is composite delamination. And we are currently working with Imperial College London and Funera Laboratory in France to develop a model which can predict the composite delamination much more closely. And we have methods within Airbus which potentially are a little on the conservative side. Obviously, when you don't master phenomena, you need to be on the conservative side, right? But we want to bridge that gap, between what is physical reality and what we simulate in the numerical simulation. So these models which we developed were kind of instrumental in the glitch-free certification of A350-900. And in addition to the static applications I talked about, we also use transient dynamic simulations to understand the impact of the dynamic events such as bird strike, hail strike, tide debris, so on and so forth, and also crashworthiness events and ditching as well. Any of you know what ditching I'm talking about?
Water.
Exactly, water landing, actually, right? So you probably can, I mean, the famous Captain Sully was able to land A320 on Hudson River, right? You probably can thank the simulation for that. And during, the post-accident investigation, I'm told that, the evidence was presented that the aircraft was indeed, developed for potential ditching. So when we generally talk about simulations, we do not really connect to the bigger picture, what impact it can actually have. We are mostly say concentrating on the local stresses, strains, so on and so forth. But I think we should also connect to the bigger picture and the kind of impact it can actually have on the aircraft program. And okay, now that I talked about the current state of the art and what the kind of success which we have achieved recently, I will take you through what is the vision. Before that, as I said, currently we are mostly using it during the certification phase and probably in service. Right? But going forward, our vision is to use advanced NLFEA during the sizing phase itself and increase the fidelity of the model gradually, because during the sizing we probably need fast reactivity in terms of as the loads evolve, as the structure evolves, as the requirements evolve. It's also important for us to be very reactive, and this is where we are kind of developing this technology to build nonlinear FEA models very fast and also adapt to the fidelity requirements as we go towards the certification. And if, as I've already talked about, the success stories kind of give us confidence that we can develop a model which potentially can replace full-scale testing. So the idea is, as you can see, to replace full-scale testing, which will lead to reduced time to market. When I say reduced time to market, it is to reduce the aircraft development time. For A350, we took more than 8 years to develop. Now the challenge we have within Airbus is, can we reduce it significantly, right? And needless to say that if we use advanced NLFEA right from the scratch, we obviously can understand the physical behavior much more closely. So we're talking about much enhanced product maturity. And if you can eliminate full-scale testing, as I said, we can reduce the cost and we can also reduce the development time. And in order to achieve it, we, as you can see here, as I said, we want to go from the classical test pyramid to a hybrid test pyramid, which we are currently working on in Airbus. As you can see, at the full level, there is no physical test, but we only have a virtual test going forward. So this is a vision which we are working towards. But one of the major challenges what we have is, as an organization, we may have confidence on our simulation. We probably can even demonstrate, the validity of the simulation. But what is also important is to get the acceptance of the regulatory bodies. And this is where, we are working on a very important framework, personally for me, Airbus, to develop an industry standard which is acceptable to all partners in the aviation industry, including the certification authorities. So it all started, I would say, probably 2017, 18, when within Airbus, we came up with this initiative to enhance the credibility of a simulation. So we used to call them as structures credibility assessment method, and we took support of a very knowledgeable industry consultant called Jean-Francois Imbert for that. And once we matured it, we, along with the senior experts Morten Ostergaard and Michel Mahe, collaborated with Boeing to release a white paper in the year 2020, and that was very well received by the aviation industry. And currently, we are developing an industry standard, credibility assurance framework industry standard, which includes, as you can see, Boeing, Embraer, and also research institutions, NASA, NIA, and most importantly, certification authorities as well, to gain their acceptance. And Tiara from TU Delft is also part of industry working group to develop this credibility assurance framework. Are we building everything from scratch? Are we reinventing the wheel? Not exactly. We are getting inspired by many technical standards which are available in the literature. The NASA technical standard probably gives a lot of recommendations in terms of demonstrating credibility. We also have predictive capability maturity model from Sandia Labs. We also have ASME, VNV, verification and validation guides to support us on this. So the idea is to develop a means which industry can use to demonstrate credibility of advanced nonlinear simulations as a potential certification means of compliance and eliminate or reduce testing going forward at least. Right? So what is the scope? Probably what is very important for us is to understand what will be the scope of this industry standard. Will it completely change the current certification means of compliance? Probably no. So we are talking about two means here in terms of credibility assurance frameworks. So one is when you want to increase the physical behaviors and the structure characteristics which you want to represent using advanced NLFEA, or when you want to reduce the physical testing which is currently accepted with the authorities. So that is either to use existing analysis testing means of compliance, but to represent much enhanced physical phenomena, or to reduce the physical testing. In our case, as I said, potentially if you want to eliminate physical testing, CAF probably will have to be applied to gain acceptance of authorities. So I'll probably very quickly take you through what this credibility assurance framework is all about without really taking a lot of time. You probably can see, you carry out any projects. I'm pretty sure all of you are working on simulation projects, right? If you look at the phases, one, you acquire what are the requirements, understand what is the problem statement, what is of interest, the stakeholders. Then you develop the model. In this sense, you design the model, then you develop and validate, and then you finally apply it. Phases are very similar, right? But credibility assurance framework recommends a lot of strategic tools. First one is called criticality assessment. This is to kind of help understand how much rigor the analyst should place on developing such detailed models if you want to eliminate testing or reduce testing we are talking about. Here there are two metrics which needs to be looked at. One is what is the influence of your simulation on the decision which you're going to take. Say you're developing a model, you have physical testing and you have virtual testing both. And virtual testing is only supporting a physical testing. So the influence of simulation is not so much, right? Because you still have a supporting means. But if you're only using simulation to design, then possibly the influence is much more. And if you're talking about a structure such as a wing, so and so forth, which is a primary structural component, then the design consequence will also be very high. So depending upon how critical the structure is and what is the influence of modeling and simulation in taking the decision, we probably will come up with a criticality score. So higher the criticality score, the more the rigor we probably need to place in terms of carrying out the modeling and simulation. And another important one which I would like to probably very briefly take you through is called phenomena identification and ranking and maturity assessment. Probably we do that in our brain when we develop a model, saying that okay, out of 20 odd phenomena, okay, this is important, but probably we may not do it very structured in a very structured fashion. This is what will help analysts to do it very methodically. It's like listing down all the phenomena which you can think of which are relevant to the problems you are solving, and try to understand the importance of it. And the ones which are very important, you probably need to understand: do you have a simulation method, and is it previously verified and validated to represent that physics properly? So importance and assessment of capability will help us understand, are we in the position to simulate the structure properly or not? And once you figure that out, and if you see that capability probably is not in line with the importance, then you need to understand what is the gap between the simulation and the methodology, right? That obviously leads to gap summary, and potentially probably may mean that you may have to develop new methods. You may have to probably verify and validate the methods going forward. So I would recommend you probably to use this in your projects as well, probably to make it much more structured in terms of how you represent physics and predict the realistic structural behavior. So I will probably will not take much time, but I would like to also emphasize a lot on verification and validation. According to me, it is of paramount importance. You develop a model and you directly go to the application domain. And I mean, I should not probably say that, but in my experience of interviewing people, for potential positions, what I see is that in academia, the focus on verification and validation isn't so much. I'm not saying that there isn't any, but possibly students probably need to focus much more. This is where you are ensuring that your model is the right representation of physical behavior, right? So as you can see in the verification, we also check whether the input data is of the right standard or not, right? Then you have computational model verification, code verification, which code are you taking, how credible it is, and the calculation verification. So we talked about the mesh sensitivity, so on and so forth. We are talking about calculation verification, and as part of credibility assurance framework, which we have thought a lot about, is to recommend something called physical plausibility checks. In fact, this is something new in the credibility assurance framework, which potentially you may not see in other standards. Here, we recommend the analyst and potentially a group of subject matter experts within the organization to critically think: is the model behavior in line with what we expect? Probably based on your previous experience, or potentially could be in terms of critical locations where you may predict hotspots. So this is from the verification point of view, and on the validation point of view, it's also important for us to understand what is the validation metric you're looking at when you compare physical testing and simulation. Is that metric accepted by the certification authorities? And finally, sensitive analysis. This is mostly in terms of understanding the different phenomena, physical phenomena, and structural behavior. We talked about imperfections. What is the impact of that on the structural behavior? What is probably an impact of friction? What is the impact of interference? We can list down all the different phenomena. In fact, all the phenomena which have listed in the phenomena identification table, whichever is highly important, understand the importance of it. Probably you can do a DOE, so on and so forth, to understand. And this is something we do in industry, and place a lot of importance on sensitivity study. But having said that, if you ask me, is it the state-of-the-art method to do so? Possibly no, because we probably can use uncertainty quantification and management. Coming to uncertainty quantification and management, as long as probably you can develop a surrogate model, it is very easy probably to propagate uncertainties across the scales. But when we want to implement uncertainty quantification at the component level, where we are talking about, say, more than 30 million degrees of freedom, where it takes days to analyze, and if you want to say carry out, say, 10,000 simulations to kind of, understand the impact of these uncertainties, it is unfeasible. We probably need to think of more intelligent means. We are currently in Airbus, looking at, directional sampling methods, so on and so forth as well. And this is where I would say, we are planning to sponsor a PhD and collaborate with academia to further improve uncertainty quantification and management technologies which we use in Airbus. In fact, in the recent CAF workshop which happened in TU Delft, rightly sponsored and very well sponsored by Kiara, when we discussed with the certification agencies, there was a clear message. If you want to eliminate full-scale testing, the organization should be capable of applying uncertainty quantification at the right level. Don't apply it, then regardless of how good the validation is, there is a real possibility that we may not meet the requirements in terms of credibility. So this probably is extremely important for us, and we are placing a lot of focus on this going forward in Airbus as well. And what is also probably more important is once you have the validation, you define a validation domain and apply your model within that validation domain. Generally, we validate probably using a different testing, and then without probably understanding what is the structure, what is the loading, what is the different physics, we probably may apply to a different, physical domain. So this tagging between where we apply and for which domain we validate is extremely important as well. So that probably sums up the credibility assurance framework, and the industry standard currently is still in progress. Hopefully, we will develop it and release it to the industry and to the outside world. So having talked about the credibility assurance framework within Airbus, as I said, the smarter testing and simulation is a marriage between physical testing and numerical simulations or virtual testing. And these two departments were actually working independently with each other. I mean, they were completely independent, right? The idea is to now integrate them, and we are kind of developing digital platforms within Airbus to seamlessly integrate, the physical testing and the virtual testing, and also integrating different domains such as design, stress, so on and so forth. And this data continuity and having a single source of truth probably is extremely important to understand the kind of validation we have between the physical structure and the numerical structure, and finally take the right decision in terms of do we have the capability to represent the structure properly or not. So that, I would say, concludes my talk, and in the nutshell, I just would like to let you know that at Airbus, over the last 1.5 decades, we have used nonlinear FEA simulations extensively, as you have already seen, to solve some of the most challenging and complex structural problems, be it on A380, A320 Sharklet, many in-service issues as well. And if any of you are planning a career in this, we'll be more than happy to welcome at Airbus. And as I said, we have a vision to establish it as a credible alternative to physical testing through credibility assurance framework, developing digital platforms. Probably one technology which I haven't talked much about is usage of artificial intelligence and machine learning. Probably I can talk about it in the future, but we are currently working on machine learning based physics informed neural networks, right, to reduce our dependency on high fidelity models, but use low fidelity models to kind of augment the physics using these physics informed neural networks. Probably just to mention about it in a couple of sentences. So in the nutshell, we are working on our vision internally within Airbus and collaborating with industry experts, academia, to cause a step change and a paradigm shift in the way we potentially will design and certify our next Airbus aircrafts. So thank you very much, and I hope I was able to at least keep you guys awake. So thank you very much. If you have any questions, I'll be more than happy to answer. Yeah, please.
Whatever you have shown, it is shown static test. What about static test? Can we avoid that? Airbus is working.
Yes. So whatever I've shown actually is for static tests, and I think we need to be humble. Fatigue is a very complex phenomenon, and we are not thinking of eliminating fatigue tests in the near future. We still need to master many aspects of fatigue, and the moment we think we have mastered, we have news coming out of fatigue, right? So currently our plan is to probably use credibility assurance framework to eliminate the static test first, and then possibly once we master, we can probably go to fatigue as well one day. But as of now, you're right, we are only limiting the removal of physical test to static physical test.
So no crashworthiness either.
Crashworthiness is already eliminated. We don't use physical tests anymore. Crashworthiness, I think the senior expert community has worked extremely well, probably between 2005, 2010, and we already agreed with the EASA that we will not carry out any crashworthiness unless it is a completely new structure wherein you have new physics, new loading, new materials, and so forth. Right. So the first thing I would like to, this is exactly what many students ask me. Okay, I can tell you what softwares we use. Okay, we use an Astran, in the linear domain, Abacus in the non-linear domain, but the focus should not be on softwares. The focus should be on understanding physics, understanding the nuances, the nuts and bolts of what goes into the simulation. And software is all about probably a month of training, right? And as you apply, you would probably master it. So this is what I generally, even during the recruitment, this is what people say, that the moment they realize that probably they're not doing so well during the interview, they say that no, I have this knowledge on this software, that software, so on and so forth. But that's not what we really give emphasis. We know that okay, and the guy who is coming in, say from an ISC or an IIT, is probably is brilliant enough to probably learn any software in a month's time or 2 months' time, and we have very well established best practices, methods, which will be kind of very easy for people to upskill themselves on the tools part of it. So my recommendation would be to focus more on physics, not so much on tools.
Hello, sir. Yeah, am I audible?
Yes, please go ahead.
Yeah, so
can you introduce yourself and then ask the question?
Yeah, hi, I'm Abhishek. I'm actually a part of the NMCAD Lab. I'm an MTech student at IC.
Okay.
So I come from a structural background. I have like 10 years experience in ISRO. So basically, I'm coming from that angle. Generally, when we undergo testing out here, we are more or less looking at the uncertainties between what has been designed and what has actually been manufactured. We're testing for workmanship mostly. But the moment we go into just a simulation based, qualification, are we not eliminating the the workmanship errors that could occur in a structure?
I would say great question. Say when we talk about uncertainty quantification, we need to understand what are the kind of uncertainties we have. We generally bifurcate them into aleatory and epistemic. So aleatory uncertainties are those which will exist, you cannot eliminate. You probably can reduce the range of uncertainty. Say you talk about geometry, you want to manufacture it to say 5 mm, you cannot do it, right? You manufacture say thousands of it, there will be tolerance. So these are kind of aleatory. You probably can, by going for more precision, can reduce it, but you can eliminate. So this is an aleatory part, and that probably may even come up from workmanship. As you rightly said, the manufacturing, tolerance. Every machine has a tolerance. Every machine has release point, as we all know, right? And then there is another one called epistemic uncertainty, which is actually because of lack of knowledge. We do not know that it exists. It potentially could be, a potential imperfection. Let's say we may think that okay, the structure what have developed. If you ask the manufacturer, say no, it's absolutely perfect. But you need to account for potential uncertainties. In fact, we do simulations within Airbus, wherein we keep imperfections across the structure. Regardless of whether it really occurs or not, we account for those imperfections. In fact, I was actually talking to someone on manufacturing errors, right? It could be ply element, it could be out of plane imperfections, it could be porosity, so on and so forth. So we account for all these during the certification phase to demonstrate our capability to withstand ultimate loads on the static side. And on the fatigue side, to be very honest, they can be very detrimental. So this is where we classify structures in Airbus called primary structural elements, which probably are extremely important. They're primary load carrying members in the aircraft. And this is where I think we use high precision manufacturing to model or to manufacture those components. Other components probably which are not so important from say flight and landing point of view, probably we can reduce accuracy, but this classification helps us to emphasize properly on key components, I would say. So in a way, to answer your question in a nutshell, we should consider workmanship errors, but there is always a possibility to what extent we can consider, and there is always a possibility that we may not be aware of what's happening in the manufacturing. So if you ask a simulation engineer, I may not really know what's going wrong in the manufacturing. And this is where, as I said, smart testing and simulation, the physical testing guys, the manufacturing guys, simulation guys, they need to work in tandem. The digital platform what I talked about, the design, stress, manufacturing, everybody comes together in defining these phenomena which potentially can go wrong. So does it answer your question?
Yeah, I do understand the logic of the answer. Yeah, that does answer too.
Okay, sure.
No, just a quick question. So when you were showing how it's evolving the curve for the simulation, so the only difference is in the time. So you want to shorten the time?
Okay, so in terms of scale as well, this one you're talking about?
No, there was one that evolved.
This one?
No, it was a blue and then it became pink, or vice
No,
versa.
towards the end.
Towards the end.
Full model is here.
This one? Okay.
The curve.
The curve.
You're trying to advance.
Okay, got it. Understand. I'll show you. It has been hidden by animations. So this is
that one.
So this is what we currently use in terms of application of advanced.
So the difference is only that you want to accelerate, or there is other.
Start using it from the sizing phase itself. So currently we use linear FEA probably till the end of MG5, even though we use to probably analyze some complicated joints and so forth. But if not, it is mostly the linear conventional techniques which kind of dominate here.
Yeah.
And we use advanced NLFEA mostly to validate the structure.
Yes.
Now the idea is not to use it only for validation, but to use along with the sizing. But this is a phase wherein we need to be very reactive because the requirements evolve, materials evolve, material properties evolve, loads evolve as well. So we need to be very quick in terms of modeling. That is the reason why the idea is to have lower fidelity models to be used here. But at the same time, ensuring that we represent the right physics. And as we go toward the certification, we enhance the fidelity so that we are much more closer to the reality, and then potentially use those high fidelity models to eliminate those cases.
But it's also the phase where you need more testing.
Testing is probably done, in this phase. Yes. Yeah, for sure. And there's extensive testing done across the. Let me show you. Yeah, you can see a significant testing, done at the coupon level, feature level, panel level. So this is where, as I said, we have this multi-scale analysis approach wherein we use coupon level tests to characterize materials, detail levels, features to probably understand, how bolts work, how interfaces work. Then we have panel levels to mostly validate those methods, and then finally use some component others to mostly validate the simulation, as you can see. So in a way, we are going from design-level generation and structural validation to understanding structural uncertainties and develop methods and simulation validation. And it's a simulation which will be used to validate the structure. Any more question? Thank you very much. Thank you, Professor.